Let me call attention, as Rob has done, to the large co-author group. These people were heavily involved in this. This project could not have been done by one person or two people or even three people. Why is that? Well, and those of you who were co-authors should treat this as a team meeting. If there's anything that you'd like to change, augment, whatever, just let me know. We actually looked at 46 textbooks. At one point, we made a kind of a census and classification system for every exercise. Amazing. It turned out actually the exercises were not as interesting as the contents, but we expended a lot of time and effort on them. It was a time-intensive piece of work. We got our basic list of these college algebra books from the monthly. We looked through the monthly issue by issue in the book review section to see if they were reviewing anything that was a first-year course or a college algebra course or whatever. Titles can be very misleading. For example, I always wondered, what does higher algebra mean? What does advanced algebra mean? Answer, what you want it to mean. Let's go on. There was a previous talk that some of you may remember, which covered the years 1892 to 1909. And it was amazing to me that not very much happened in the way of new ideas in content in that time period. Even though there were many, many recommendations by learned committees and distinguished commentators as to what should be done differently, but the authors, you could say they ignored it, but I don't think that's correct. I think maybe it's a combination of ignoring it and mulling it over, because as you will see, starting in 1910, all of a sudden, new ideas were all over the place. Now, it takes ideas time to, I don't know, what do they do? Ferment? Okay, so I talked about that last time. Let's see what happens now. I'm very fond of the idea that even something as detached from everyday life as mathematics is actually influenced by the social and political context around us. I cannot point to a single thing where there's documentary proof of this, but it just makes sense to me. And in this era that I'm speaking about in this talk, it overlaps greatly with the progressive era. And some of the things you'll remember from high school physics, not physics, civics. A lot of progressive stuff, except that this is about prohibition, of course. Okay. I couldn't help including this cartoon. In case you can't really tell, the guy on the left is holding up a Swiss Army knife. So I think of that first era that I talked about in my previous talk, 1892 to 1909, as the traditional era, and this is the new ideas era. It's always nice to have eras and names for eras. But I have to tell you, the idea that 1930 is a natural ending for an era isn't actually so. I mean, there's a certain point at which you run out of energy. And also, we were tremendously helped by the fact that for much of our work, the books were in digital form in Google Books. But around 1923 or thereabouts, we were dependent on interlibrary loan, and it just slows everything down. So anyhow, we ended in 1930. So here's the Venn diagram here. We've got unification. I will tell you what that is, of course, but not just yet. The general idea, though, is that you take mathematical subjects that are often presented separately, like trigonometry and algebra, and you sort of teach them in the same course, in the same book, using every opportunity you can to have one subject shed light on another. That was a category of book that came about in the era I'm speaking about. It had two varieties. Some of those unified books had no trigonometry. Not that many. It turns out, if you think about it, trigonometry is a natural thing to incorporate with algebra, and so there were a bunch of unification books with trig. Then on the right-hand side, we have books that have trig, and often a lot of it, but not unified. And everything else is traditional. And you'll see some graphs as we go along showing numbers on these various things. Any question about that? All right. The guy who starts it off in 1910, William Brenke, a student of Maxim Bocher at Harvard, and he not only did the unification, but he added 113 pages of trigonometry. That's a lot of pages in a genre of books that never had it. Never. And why should they? Because almost every college had its own course in trigonometry. Well, Brenke had an idea. So, I mean, here's a very quick example of unification. Actually, it's not an example, it's just the concept. But I'll show you Brenke's table of contents in a moment. So there's Brenke's table of contents, 19 chapters. And you can see that there isn't a huge amount of intertwining, at least from judging from the table of contents.
What did he call this book?
What did he call it? You know, I don't remember. I don't remember. Unification was not a crazy idea that Brenke just came up with. It had been discussed quite a bit. And here are some people who had been involved in creating the atmosphere of let's do unification. Felix Klein, who didn't really comment on curricular things in American mathematics that I know of. I didn't see him ever saying anything about college mathematics. But his research, he was really famous for unifying geometry. All the different geometries that flowered after the discovery of non-Euclidean geometry and the decision that, okay, that's mathematics. Klein showed how they could all be made sense of by group theory. And it was a wonderful example of a subject that needed unification, and he did it, and he became quite famous. It was one of his first research works. Eliakim Moore, in his prime, which I suppose is around 1902, when he was retiring from the presidency of the AMS, in his prime, he was probably the leading American mathematician when you combine both competence in research and having interesting things to say about teaching and about university leadership. He was the chair at the University of Chicago. Chicago was just invented more or less the time when he came along. And he was faced with, how do I take this Rockefeller money now and make good use of it for mathematics? The Committee of 10, well, you know how these committees work. We've seen them in our own era. A lot of distinguished people get together, a number of questions are put out on the floor, recommendations are written, and the key thing about them is, you know, who was involved? Were these people really influential people? And Simon Newcomb was, at this time, a very influential research mathematician. And then there was the J.W.A. Young Committee on College Entrance Requirements. All of these created what I like to think of as an atmosphere that made college algebra authors think about this. Herbart was a philosopher, a German philosopher who sometimes thought of as the first philosopher of education. I don't know how true that is, but and so these guys, Klein, Herbart, and Newcomb, were people from the, you might call, rarefied world of research. E.H. Moore, he spread all over the lot. He was quite a man. So Arnold Dresden was asked by the Bulletin to review Brenke's book. Now you need to understand that Dresden was himself a distinguished person. He eventually became a president of MAA. And you can see from the first two bullet points there, he's really not too impressed. On the other hand, he feels he has to end up by saying something nice, so he ends up by saying something nice. But you may remember when I showed you the table of contents of Brenke, it didn't seem to show a lot of intertwining, at least just looking at it on a block level. So another feature, though, of the New Ideas era is the heavy introduction of trigonometric topics. I say it's a revolution. Look at the dots. It was sudden, it was strong, and it was in the face of an existing course. So that seems to be, to me, an idea that this was not just a little tweak. And some of those page counts are pretty substantial. Look at some of those dots up there, up around 100. I didn't know there was 100 pages you could write about trigonometry, to tell you the truth. Why trig? Well, it seems like a natural thing to unify with algebra. But maybe there's more. An alternative driver, in my opinion, comes from Professor Edwin Bidwell Wilson, who has a very distinguished resume, of which I've just put a few thumbnail items on the right over there. He wrote a book review. It's down at the bottom of the slide there. In the bulletin of the AMS, he's reviewing this calculus book, and he entitles his review, "Let us have our calculus early." And he says that the courses we are teaching beginning students don't make good. Those are his 3 words. They don't make good. So you can figure out what that means. I think it means that there's no real reason anyone should want to learn this. But He thought people should be going into calculus early because calculus had wonderful applications, which it does. Now, when did students in the early 20th century take calculus? You can see the chart shows you that it's sophomore year at the earliest and sometimes junior year. It certainly is different today. In fact, in thinking about this, it occurred to me that if you want to know what was the agenda of 20th century undergraduate mathematics, you could look through all of the NSF-sponsored projects, and you probably wouldn't find anything as important, as durable, as pervasive as making calculus be a freshman course. You could say that that was a century-long project. Did anyone know it was a project? Did they have organization? Did they have team meetings? I don't think so. But something was impelling it. And I think that's a fascinating issue, which I'm only touching on here. I think it would make a suitable research career for someone who wanted to spend a lot of time on it. Now, I personally think that these books in the trig but no unification are of special interest because I'm asking myself, what was motivating them? You know, the unification people, they took trig on board because they needed a partner. Takes two to tango, so let's do trig. But there's no tango going on here. I think it was the flooding of engineering students and other applied sorts of students into the colleges. And I took the trouble to figure out who these authors were. The things that are highlighted in blue, these are authors where I could find either in their prefaces or their resumes some particular dedication to applications. And it's 6 out of 7 in this left-hand category of trig, no uni. But as far as the unified books are concerned, we have only 3 out of 7. Now, these are small numbers, I agree, and you can't go crazy about small numbers. But throughout this, I am looking for birth pangs of the current situation where we have an entire elementary course called pre-calculus. It's not unified, usually. And I'm wondering whether this genre of book somehow or other was part of an evolution that resulted in the world's first pre-calculus book, which, if I'm not mistaken, the first book entitled Pre-Calculus, I think was published in 1964, maybe. But don't quote me on that. I could look it up. How did that happen? I don't know. Maybe this gives an idea. Okay, so I want to talk about another issue that I found worth thinking about in these books. Oh, look, probability. What is probability theory doing in an algebra book? Okay, you might say, it's not an algebra book. It's a first-year math book. True. So that, I suppose, is part of the answer. But this idea of probability in an algebra book goes back beyond our project. It goes back at least as far as Isaac Todd Hunter, who was a kind of a polymath of his time. excellent in research, wrote a lot of books of one sort or another, was fluent in many, many languages. And for some reason, I put Augustus de Morgan's picture next to him because these two were friends. In addition, de Morgan was Todd Hunter's teacher. And I think these guys were somewhat involved in actuarial work. And so they understood the value of probability, and that might have been part of it. But then it just sort of continued to be there. So here's a plan of investigation. I think of the probability as an example of breadth, something different. Not focused on a particular thing like getting people ready for calculus. And then, of course, there's preparation for calculus, which is a sort of a depth orientation toward instruction. I wanted to see whether there were patterns or trends or something like that there. So we wanted to count pages for breadth, pages for calc prep, and then stew a little bit about subjectivity because, well, take, for example, continued fractions. Where does it go? One of the most essential things about continued fractions is the issue of whether the so-called convergents converge. So isn't that calculus? Well, you have to understand I was using precise definition. When I say prep for calculus, I mean it deals with an issue that comes up in calculus, in actuality, in some calculus books, or it prepares you for exactly the topic that it's meant for. Continued fractions would be a kind of a nice example of convergence, except that here's the problem. You really have to say a lot about these things before you can get the students to care, to understand, and then to care about them. And if you look at a calculus book, they're in much too much of a hurry to be going off on tangents. So at least that was my opinion. I'll grant you it's subjective. So I say, well, not really prep for calculus. Maybe it's more like breadth. On the other hand, I don't know, I could be persuaded the other way, perhaps with more evidence. And, nonetheless, here are some preliminary definitions. A prep for calculus issue should not be a high school topic. Why not? Because I'm interested in what the author is thinking in his heart of hearts. Is that where we think? I don't know. The high school curriculum, he's got to follow it. If he's going to review the high school curriculum, he knows what he's got to do, or she. Same thing with breadth. Any subject that is sometimes the high school subject, not interested in that. Also, in the case of calculus, I didn't think that diffuse effects like skill with algebra was the sort of thing that I wanted to deal with. I mean, almost every mathematics course requires thinking, which could help you in any other mathematics course. So I wanted something fairly definite. And still there is this issue. Okay, fine, you got some sharpened definitions there. Still, what goes where? Here's what needed to be classified. I don't know if I mentioned that I should have told you that there are 22 mathematical topics that are found in at least one of the books we have surveyed. I should have had a list of them, really. This is a small number of them, but there are some high school topics like basic manipulations, quadratic equations. These are the ones left over, so to speak, that we had to classify. So I am perfectly happy to accept, yes.
Back one slide just for a second. Okay, thank you.
Anything you want to bring up? No? I am perfectly happy to accept alternative concepts of what goes where and see whether the numbers come out differently. I will show you now how the numbers came out the way we did it. Well, first of all, exactly what went where. This is what went where. I wondered about complex numbers. I don't know whether any of the rest of you have the same reaction I do. Surely that's a calculus topic, isn't it? Heck, elementary algebra deals with complex numbers. You can't solve a quadratic equation half the time unless you accept the complex number. But I looked through William Fogg Osgood's 1921 calculus book. When I say I looked through it, what I meant was I used Google search facility. I put in complex number. Nothing, not a single mention. And that was true of other books as well. So it's not prep for calculus. I left a few things unclassified, mostly because, on the one hand and on the other hand, and this argument and that argument, and finally, the page counts were small enough that it wouldn't make a lot of difference if you did it differently. However, I'm perfectly prepared to run the numbers with these things included, as long as you put together a reasonable description of how they are this or that. All right, I'm not going to go through that. So now I'm looking at the breadth to calculus ratios. Page count divided by page count. And you see that there are a lot of blue things down here. The blue things are the traditional books. The books before 1910 and the books afterward that are basically just like the books from 1910. But there are very few actual zeros. See, a ratio of 1, that's so far, that's a way down here, you practically can't tell it apart from a 0. But a ratio of 1 is, I think, interesting. Now, these 4 critters up there, they are kind of hard to believe. Let me tell you, though, something about them. There were books where the ratio had a 0 in the denominator. That would make it awkward to plot. So I changed those zeros to 1s. But when you see those such big numbers, you can probably say, they didn't have any calculus prep. That's most likely true. So let's look at the trig no unification. Here's, let's see, Brenke is, he's not there. There's one way up there. Here, this guy here. That's probably about a 1. And then we've got some stuff over here, over there. There's really no pattern. People are experimenting, I guess. At least I don't really see a pattern. I don't know if anyone else does. Tom, you see a pattern? Okay, now what about unification, the unified books? Well, the first one is here. This is Brenke. And then there's all of a sudden a big jump there. Here are a couple right on top of one another. Low numbers. 0. I decided that it might be more interesting to look at some of these things like unification with this type of graph. And here, when you look at that right away, you say, oh, they didn't like it to start with, they tried it out, they didn't like it after that, that's it. Maybe, but see, this is like almost every bit of science writing you ever see in the New York Times. Somebody pops up and says, yes, but more research is needed. I'd really like to know what happened in the 1930s. And the 1930s were a very interesting decade because of the invention of the liberal arts math course. What did the liberal arts math course do to the ecosystem? I don't know. So here are some questions for research. I am wondering about unified courses, whether they might make demands on a student's memory that just are in some cases difficult, because you're asking them to remember things that seem different. And you're going to show them, oh, it's really not so different after all. Look at this. But at the same time, you know, they've forgotten about quadratic equations. I don't know. It's just a thought. Oh, so I've kind of touched on this already. So there we go. I knew I'd get a laugh. Well, thank you for your attention.
Thanks again, Walter.
So I have some comments. So it has always seemed to me that there were other societal variables than what went on in the minds of textbook writers and so on. And for people who live in our own times, we see parallels today for the lack of ability to have vastly oversimplifying computer science affect mathematics curriculum in high school. But coming to the period you're talking about, it's hard to believe that World War I didn't affect books, not only in the sense that a lot of people weren't writing textbooks, many people were going off to war instead of going to college, which was not a widespread activity in those days either. And so, and of course, by stopping in 1930-ish, it's hard to know what effect the Depression had on.
Right, the Depression is certainly not part of the story here. You should be able to see some effect maybe of the war, for First World War, but I have found that it's very, very hard to dig controversial stuff or interesting stuff out of prefaces. People do not like to bare their souls about anything that's kind of like a weird theory or a weird concept. I don't remember anybody commenting on the war, except in after the war. Hedrick, Earl something or other, Hedrick, at one point the president of the MAA, and
Whom the Hedrick lectures are named.
yes, he's lionized today in the Hedrick lecture. He wrote an article. It's not really part of this project, in the monthly, I think, in which he made remarks about how the experience of the war should be concentrating our minds about what mathematics to teach and who should be learning it. And I was amazed at this article because you don't see many like it. He specifically mentioned the problem of aiming artillery, which has a trigonometric aspect. Okay? And he said, it's all very well that maybe the people that you trained and, here stateside and how to do that, how to do whatever minimal trigonometry is needed. But what happens if the guy who's manning the gun becomes disabled or killed? Somebody else has to take over. And did you teach him trigonometry? That's basically what Hedrick was saying. He said, everybody should be learning trigonometry because it's necessary in war. I was amazed, totally amazed.
The other question I have, and it's broader than this particular period or context, is whether the reason why people wrote books in that era is different from prior times today or whatever. I mean, one of the things that fascinates me about somewhat earlier time was that every publisher had a series of books. They had elementary algebra, intermediate algebra, analytic geometry, and there were people like Charles Davies, and Robinson, and Wentworth, and who wrote these series. But these were not publish or perish. People didn't write books at that time because they needed it for tenure. Most of these people didn't have PhDs, certainly PhDs in mathematics. Many of them only had master's degrees. Many of them weren't even mathematicians.
It's not clear whether tenure was widespread either.
In any sense of the word. So, I think it's interesting to consider how much pressure for change was not endogenous, so to speak, but from the publishers themselves, and a lot of it was often good enough to write a book for a particular school. I mean, a lot of Davies' books were designed to be used at West Point, and because they were used at West Point, they found places otherwise. But there was a fixed, constant demand for his product.
I remember reading once about Wentworth's early life. He didn't really interest himself much in mathematics in his education, but he got a job at Phillips Exeter, I think, Academy a prep school. It could have been Andover. I get them mixed up. And he was asked to teach a math course, and he didn't like his book. He didn't think that the arguments were any good, the proofs were no good, the exposition was no good. He just didn't like it. And so for his course, he wrote his own notes. And before you know it, the guy has written book after book after book. And we know him as an excellent mathematician.
All right, well, let's thank Walter once again for an interesting talk.